Imagine a liquid so strange it can flow up the walls of its container with zero resistance. That's not science fiction, it's called superfluidity. Let's start with helium-4. When cooled near absolute zero, this everyday element does something extraordinary. It transforms into a superfluid, a state of matter where viscosity vanishes completely. It flows forever without slowing down. No friction, no loss, just pure motion. In our everyday world, every liquid resists flow. Try stirring honey or even water, there's always drag. But with a superfluid, the resistance is gone, forever. That's the wonder of superfluidity, and it comes straight from the heart of quantum mechanics. At these ultra-cold temperatures, individual helium atoms begin behaving collectively, forming what's known as a Bose-Einstein condensate. Instead of moving as particles, the atoms act as one giant quantum wave. This collective behavior allows the liquid to do things that break our classical understanding of physics. Superfluidity is a cousin to superconductivity. Where superconductors allow electricity to flow with no resistance, superfluids do the same with motion. They're both part of the quantum family, where the rules of the everyday no longer apply. So what makes superfluids so bizarre? First, zero viscosity. In a famous experiment, scientists spun a ring of superfluid helium, and it kept moving forever, no slowdown. That's impossible with normal fluids. Then there's the fountain effect. A superfluid can spontaneously flow up and out of a container as if defying gravity. It's driven by quantum pressure and temperature gradients, completely unlike any behavior in classical fluids. And then there's second sound, a quantum wave that travels through the superfluid, not as vibrations of atoms but as waves of temperature. Yes, heat itself becomes a wave. Now let's talk applications. Superfluid helium is already used in MRI machines and ultra-sensitive gyroscopes. But scientists believe it could go much further, enabling powerful quantum computers, creating frictionless transport in microfluidic devices and powering some of the most precise sensors on Earth. And that's just the beginning. Researchers are now exploring superfluidity in ultra-cold gases, neutron stars, and even inside graphene. New materials are showing signs of superfluid-like states, at higher temperatures and in more complex conditions. Imagine superfluid coolants in spacecraft, or energy systems with zero-loss efficiency, or biocompatible technologies that use quantum flow to interact with our cells at the nanoscale. Yet even with all we know, superfluidity still holds mysteries. How exactly do these transitions happen? Can we create stable superfluid systems at room temperature? What does it teach us about the universe? Superfluidity isn't just a scientific curiosity, it's a quantum frontier, a doorway to understanding matter, energy, and motion in ways we've only begun to imagine. This is the strange world where liquids don't just flow, they transcend.